Hello, my name is Muhammad Izzat bin Muhammad Azhar and my student ID is 21001270. I'm from group 2.
Hi, I am Ahmad Azwanzi bin Samsul Bahrain, student ID 21001915.
Hi, my name is Nelly Carey with the student ID 201819.
My name is Siti Sarah Chu, metric number 201118.
Hello, my name is Iqbal Daniel Belna. My student ID is 21001181. So I am from group 2.
Under the Reaction Engineering 1 course, I will firstly talk about the steam methane reforming overview. There are two main reactions involved in this process, which is firstly the steam methane reforming, which is SMR, a reversible endothermic reaction that takes place at a high temperature. The second one is water gas shift reaction, which is WGSR, a reversible exothermic reaction. Next, for the type of reactor, packed bed reactor, which is PBR, is widely used for SMR process. This is because it requires small volume to achieve high convergence, and it is also low in operation cost. It requires a high surface area for efficient contact between the gas reactants and solid catalyst, and it operates continuously. Since the reactants are in gaseous state, PBR is suitable for this process. For the type of catalyst used in this process is nickel alumina catalyst because it has high surface area and active sites to accommodate high activity. It is also low cost and it provides stability for reactants at higher temperature and pressure. Now here's the operating conditions for SMR process.
The next part I'm going to discuss is maximizing the selectivity and yield of hydrogen in the syngas. So the main focus is to optimize the SMR reaction in the whole SMR process. Any change that is done on the SMR reaction has a significant impact on the entire process compared to changes done on the water gas shift reaction. Ways that you can improve the SMR reaction include increasing the concentration of methane in the natural gas inlet, as well as increasing the temperature because SMR occurs at higher temperatures. You can also keep the pressure constant while increasing temperature, but you can also increase pressure so that you increase the temperature, the concentration of methane in the inlet gas. Moving on to the next part is to determine the size of the reactor. The PBR sizing was done through the symmetry simulation at the PMS, together with the PMS part section of this project. How we did it was estimating the size of the catalyst in terms of diameter, estimating the packing of the catalyst along the PBR length, and then assuming that the pipe was a schedule 5 pipe with a 30-inch diameter. And when we did the simulation, we got a maximum length of between 10 meters to 100 meters to achieve 73% conversion. The last part of this section is purifying the syngas. The gas mixture entering the water gas reactor is not pure hydrogen, and therefore it needs to be refined further to meet customer specifications. Pressure swing absorption is the most common industrial setting. The gas mixture enters a purifier where specific absorptive materials trap contaminants at high pressures. Some of the contaminants include carbon dioxide, methane, carbon monoxide, and water. Purified hydrogen is then pumped out of the vessel, and finally the vessel is depressurized to release trapped contaminants.
So, for separation process, the case study for separation process 2 is to remove the contaminants, which is CO2, N2, and H2O from the raw natural gas. The composition and conditions of raw natural gas was already given in the table 1 in the question. Before proceeding to the next reaction process, this raw natural gas will go through a few separation process to reach the conditions and composition listed in table 2. Before proceeding to the next reaction process, this raw natural gas will go through a few separation processes to reach the conditions and composition listed in Table 2. Next is the membrane characters or the selection of the membrane. So for the type of membrane, our group choose spiral wound model, which as it has a greater permeance and is more resilient in heavy operating conditions. Next, for the membrane material, we use glassy polymer because it is better conducted on particle size that condensability. For the membrane structure, we choose composite membrane structure, which is cheaper, better mechanical support, and separation capability. For the composite structure, we use spirally wound cellulose acetate. From the block diagram, as you can see, there are four components that we use, which are two-phase separator, membrane, mixer, and component splitter. The unit operations operate isothermally and in constant pressure, hence maintaining the temperature and pressure at 70 degrees Celsius and 70 bar respectively. From the analysis of membrane characteristics, it is not possible in more than one phases, and because of that, the two-phase separator need to be installed as pre-treatment of the raw natural gas to ensure that the liquid water is removed and only the gaseous mixture is allowed to enter the membrane module. It is assumed that all water in the stream is in liquid, and after the flash separation, the overhead evaporative stream which contains the methane, carbon dioxide, and nitrogen is directed into the membrane module. The bottom liquid stream exiting the two-phase separator is channeled to a component splitter where the amount of water as stated per the specification is split and channeled to the rotated stream and combined in a mixer before being channeled to the stream methane reforming process. As we can see here, that from the block diagram, they are separated. And for the upper stream, which is the vapor stream, the composition or the flow rate for CO2 is 26.517 kmol per hour, nitrogen 16.91 kmol per hour, and methane are 236.466 kmol per hour. And for the liquid stream, which is the below stream, there is only H2O, and the flow rate is 20.826 kmol per hour.
This is the experimental data that we get from a journal that been written by Josh et al. In 2016. So the experimental consists of permeability of CO2, CH4, and nitrogen, also permeate pressure and also fluid pressure, the membrane thickness, selectivity, and pressure ratio. For the mixing model of the membrane unit, since the methane and nitrogen has the same permeability, so it enables us to analyze the stream entering the membrane as a binary mixture. So as we can see from the diagram, there is a feed stream, the transited stream, and also the permeate stream.
So, I, Iqbal Daniel, will further continue to the process modeling simulation part. So, in the introduction, we have constructed the three main objectives. The first is to develop the component balance and the concentration profile. The second objective is to simulate the whole production of the syngas, and the third objective is to understand how temperature, reactor size, and feed influence towards the simulation by using the case study function. This is our overall plant model, which contains the mixer, plug flow reactor, cooler, and the packed bed reactor. The assumption that we make in the reactor is all the components in the reactor are in perfect mix, the reactor have no work involved, density is assumed to be constant, and the potential and kinetic energy are negligible in this reactor. The first reactor that we use in the plant is the plug flow reactor. From the mixer, the stream go to the plug flow reactor. This is the specification of the plug flow reactor that we use in the symmetry software. Beside the plug flow reactor, we also use the packed bed reactor for this plant. After the stream leaving the plug flow reactor, it enters the cooler unit to cool down its temperature before entering into the inlet of the packed bed reactor. Below, this is the specification of our packed bed reactor that generated from the symmetry software. Next, we move on to the case study. There are three case studies that we would like to study about our plant using the symmetry software. The first is to study the effect of steam pressure towards the final carbon monoxide flow rate. When the pressure increases, it will shift the equilibrium constant to the left, which is toward the reactant, and decrease the carbon monoxide production as the final product. According to the Arrhenius equation, the higher the temperature, the higher the rate of reaction. This will result the more carbon monoxide being converted into hydrogen and will decrease the final molar flow rate of the carbon monoxide. And the final case study is to study the effect of PFR length to the final carbon monoxide flow rate. The higher the volume of the PFR reactor will increase the will give the higher conversion rate. This will increase the more carbon monoxide and hydrogen being produced.